Hi, my name is Manish Gupta, and in this video, I'm going to talk about Frugal prompting for dialogue models. This is a recent work which we did in collaboration with IIT Kharagpur, specifically Bishal, Abhinandan, and Professor Pawan from IIT Kharagpur, and Sakya and myself are from Microsoft. So let's get started. LLMs, large language models, are great. In fact, in-context learning-based LLMs have actually changed the entire field of NLP in recent times. However, much of these, many of these LLMs, GPT-3, Codex, Lambda, Palm, are all closed source, and they are available as APIs. And the billing by these LLM inference APIs actually depends on the input and the output size, combination of the two, right? So therefore, a natural question is, how can we design prompts to increase the LLM performance, but reduce the prompt size? Of course, we want to keep the cost low. So therefore, we want to reduce the prompt size, but then we want, of course, awesome accuracies for whatever task we want to use the LLM for. Specifically in this work, we focus on the dialogue modeling task. So it is basically like a chatbot kind of a task. So how to use LLMs for chatbots in a very, very frugal manner, in the sense you want really awesome answers being generated, replies being generated, but then at the same time, your prompt size should be as small as possible. So in this work, we make three important contributions. We basically study the effectiveness of various in-context learning models and input formats for dialogue modeling task. Second, we propose a new metric called as UID, usable information density, which I'll talk about in this video in detail, to capture trade-off between accuracy and length for various input format and the in-context learning model combinations. And third, we basically experiment with two data sets, MSC and TC, and also four different in-context learning-based large language models, GPT-3, FLAN, T5, T0, and TK Instruct. So there's a lot of related work in the literature, around two important topics: LLMs for dialogue modeling and how to optimize the computation for large language models, right? So specifically for dialogue modeling, several LLMs have been proposed: Dialog GPT, Plato, BlenderBot 3, Mina from Google, Lambda. These are all popular dialogue modeling architectures. Some of them are actually pretty large in size, like BlenderBot 3 is 175 billion, Lambda is 137 billion. They're compute intensive to fine tune. Next, basically, there have been like in-context learning based models like OpenAI's TextDaVinci 003, which has been trained using RLHF kind of mechanisms, reinforcement learning with human feedback, right? There have also been smaller kind of models which are more open source in nature. So models like T0, FLAN, TK Instruct. The problem is that, they suffer from increased inference cost due to large prompt sizes. So if you have very large prompt sizes, especially for dialogue modeling, you may want to basically give the entire dialogue history as an input, right? And there could have been like several turns that might have happened in the entire conversation so far. So that basically incurs a lot of input. That basically means that the prompt size is too large, and therefore it incurs a lot of inference costs. Now, to reduce inference costs, people have done a whole bunch of work in the LLM community. So first, people have actually studied the environmental impact of these large language models, fine-tuning and inferencing in terms of the CO2 emissions. And to make these inference step efficient, people have typically come up with two kinds of models or two kinds of approaches. The first one is model distillation based method. So you have a large teacher, but the small student, try to have as much accuracy as possible, but then you have a small student, so therefore the inference cost is smaller. The second thing that people have done is to use efficient transformer architectures like reformer, linformer, BigBird, and longformer, which try to reduce the quadratic complexity to something closer to linear complexity, so as to reduce the overall inference costs. Right. So these are possible when you have open source models, but with closed source models like GPT-3 and GPT-4 and so on, you basically cannot use model distillation or efficient transformer kind of architectures. You don't have a handle. These are black box kind of settings. Right? So now let's focus on the dialogue systems kind of the task. So there are four main kinds of things that you want to supply as part of a prompt in a dialogue system. Imagine a chatbot system. What kind of prompt would you write to ask GPT 3.5 to generate the response in a conversation, right? So first is task instruction. You have to tell GPT that, hey, the task is a dialogue response generation task, and you are a chat assistant, and you have to help here, right? The second part is dialogue context. So you may want to supply the entire dialogue history, the entire conversation that has happened so far. You may also want to give some background information. For example, if you know about the user, you can actually give a fictional representation of a user. So you could say basically that, hey, this user is a very shy user and or a very terse user, and therefore generate stuff based on that persona of the user, right? Or you could also supply information about the conversation, specifically like knowledge sections, which are more like paragraphs related to the topic of the conversation. This is more like metadata associated with the dialogue. Either it could be associated with the user or it could be associated with the actual conversation topic. Okay. The third thing that you want to give as part of this prompt is person one's latest utterance. So what did the user just say? Person one being the user and person two being the bot. So what did the user just say? And then you want to basically reply to that, right? And then, of course, you can actually give exemplars. So you could basically, in context learning setups have been shown to perform really well in few short settings. So you can give some exemplars, which can in turn include any of these things. Okay. Here is a sample template, where you have a summary of the conversation being provided as extra as an input. So rather than passing the entire dialogue history, here summary is being provided. So here is a summary of the conversation between person one and person two. And it's a good summary. Person one wants to go back to college to learn more about accounting. Person two wants to study. So this is what they have discussed so far, right? And then here is so this part of the template. This is an actual instantiation of the template as a prompt, right? So here is the task instruction being provided. So based on the dialogue between person and person two so far, try to anticipate what the person's two response might be to person one's next statement. So this is basically the task instruction part, right? So this is the task instruction part. Uh, this is basically the dialogue context part. So dialogue context provided as a summary, right? And here the third part at the bottom is essentially, whatever the person one said now. So this is basically the latest utterance part by the person one, right? And then the model is supposed to is basically prompted with person two token, and then the model is expected to generate some good response R. Okay. Now, it also turns out that rather than giving the entire prompt, one way of reducing the size of the prompt is to actually use perplexity prompts. You see easily, I mean, these prompt sizes can get very large, especially if you're not using the summary, for example, of the full dialogue history and so on, right? So to reduce the prompt sizes, people have experimented with something called as perplexity prompts. Okay. So you could basically, therefore, experiment with manually designed prompts or perplexity optimized prompts. Let's talk about both of them in this slide. So manually designed prompts, essentially the idea is that you need to come up with a prompt such as to avoid repetitive or dull responses and maintain consistency with respect to the current utterance and the entire conversation so far, entire dialogue context. Okay. So here is an example of a manually engineered prompt template, right? This is basically a one-shot prompt template. So essentially, you first have an exemplar here, and then this is the actual task, right? So this is an exemplar at the top, and then there's the actual task. And here, so here is the task description. So learn from the example below how to generate consistent and diverse responses between person one and person two, right? So, and then the input dialog context. So actually you're passing on background information about both person one and person two. And then you're basically saying this is the summary of the conversation so far. So that's the dialog context. And then you're basically saying here is the, this is the task instruction repeated again. And this is what the person one just said. So person two, this is the expected response. Remember, this is an exemplar, so you actually provide the response also as part of the input. Okay. And then you say that, hey, exemplar is done. Now try it yourself. So again, of course, for the actual task also, you provide the background information for both the persons. And then you say this is summary of the conversation. And then you say this is the task. And then, the user just said this. So what is it? What is the response that the bot should generate? Okay. So it's a manually designed prompt template with the summary of dialogue history, persona, and the latest person one utterance as the dialogue context with one exemplar. Okay. Now you could also do, so this is the manual design prompt. Now you could also do perplexity optimized prompt. So what is the perplexity optimized prompt? So this is a prompt, the basic idea is that a prompt is great if it basically scores low perplexity on your LLM, right? Low perplexity is good, by the way, right? Remember, perplexity lower the better. So the idea is that a prompt is good if it scores low in terms of perplexity using your LLM. But hey, you have just only one prompt. So basically, how does low perplexity help, right? So the idea is you take your prompt. So you take your manually engineered prompt, which is this, and you basically instantiate with say 100 examples. So, you basically, instantiate with 100 examples. Okay. So you have basically like 100 examples so as to compute perplexity of the response that you generate. Okay. Now, or rather, sorry, you take those 100 examples and get the perplexity of the entire prompt itself using the LLM. Okay. Perplexity of the entire prompt itself using the LLM. Now, what you can also do is to take this entire prompt and ask for paraphrasing. So ask GPT, hey, can you paraphrase it? Or you can actually do back translation also. So you can ask GPT to translate it to, let's say, French, and then ask it to back translate it to English. Okay. So that is how you can generate paraphrases. So let's say you generate like 5 paraphrases of this. So essentially you have like the original prompt plus those 5. So you have like 6 different templates, right? And for each of them, you have like 100 instances. You evaluate across these 100 instances, which of them gives the lowest perplexity, and you choose that template. Okay. So in general, you're basically trying out several templates. You're not manually engineering all of them, just to engineer one and then try out paraphrases. So try out several templates and choose the one that the LLM thinks is the good one, right? Lowest perplexity one. Okay. So that's another way of reducing the size of your prompt. Typically, perplexity prompt optimized templates are essentially shorter, in nature. Okay. So you can also optimize for how do you want to use the dialogue history input. So I mean, as such, there are a lot of redundancies in conversations. So there is back channeling, there is clarifications, there is mistake correction. Somebody tries to correct somebody's mistakes. Back channeling basically meaning somebody interrupts somebody else in the conversation and so on. So all of that is a natural part of conversations. But maybe our dialogue models like GPT-3 don't really require all of them, right? So therefore, we can actually try to reduce the size of these conversation history. Okay. Also, in the conversation, one of the person who is participating could be just the model itself, dialogue model like TextDavinci 003. And TextDavinci 003 is known for generating elaborate and long responses. So therefore, all of these long responses need to be shortened so as to reduce the size of the prompt, right? Now you can do shortening in several ways. So you could do either by doing selection of the dialogue history or summarization. So by selection, I mean, maybe 100 turns have happened between person and person two so far, but then you can just take the last 4 turns. So that's called recent K. Or you could basically take the semantic K. So, if the user types some query, well, you try to figure out 4 terms which are very similar, or four utterances which are very similar to this user utterance. Okay. Similarity can be obtained using various methods like SimCSE or sentence transformers. In this particular work, we take the average of those similarities and find semantically related utterances, which we include as part of the dialogue history. Okay. You could also summarize the entire dialogue history using various models. So we specifically tried 3 different models to actually summarize the entire dialogue history of the conversation so far, which is basically BART-D as a model, which is basically a model, BART model, BART large model, in fact, fine-tuned on the dialogue sum data set. That's also a conversational data set. So we fine-tuned it on, on the dialogue sum data set, 12-layer encoder, 12-layer decoder model, BART model, and that generates a good summary of the entire dialogue conversation so far. Okay. Pegasus CD is Pegasus DS and Pegasus CD are Pegasus models. They're fine-tuned on different data sets, so CNN, Daily Mail, and the Dialog Sum and Samsung. And they are slightly larger in size, 16-layer encoder, 16-layer decoder. Okay. So that's that. So that's how you can actually reduce the dialogue history input. Well, you can actually also reduce the size of the background information. So background information, remember, persona-based information or the topic paragraphs related to the conversation. Well, you can reduce them as well by using BART or Pegasus models as summarizers. Okay. In this work, we actually experimented with 2 different data sets, multi-session chat and topical chat data sets. So both of those data sets are, of course, dialogue modeling data sets. In multi-session chat, you have multiple chat sessions whereby the speaking partners, person 1 and person 2, learn about each other's interests and discuss the things they have learned from past sessions. So think of somebody you meet randomly in a bus or a train, and then you start a conversation between them. You try to understand what their interests are, and then you start discussing with them, right? That's that. Topical chat here, each pair of users is assigned a topic, 1 or more topics, along with some facts or knowledge about the topic, these Wikipedia paragraphs or some paragraphs from some other sources. And the users are asked to have a conversation about the topic. For example, what do you think about Hamas and Israel things that are going on, or what do you think about the Cricket World Cup, which is going on, and so on. Okay. So in MSC, each user is asked to play a particular role. So, when you have these chat sessions, each user is told that, hey, this is your persona. This is the role that you have to play in the conversation. In topical chat, well, the background information is about knowledge sections associated with the conversations. People are told, hey, this is the topic and these are knowledge sections. This is what is going on between the Hamas and Israel story and so on. And people are supposed to talk based on that information. Okay. So both the data sets, the test sets are pretty good, pretty large in size. So 16,300 or so context pairs there, and about 7,500 context pairs in the other data set. Also, the conversations are pretty long, about 12 conversations, 12 utterances per conversation here, and about 20 utterances per conversation in the topical chat data set. Okay. So we tried to experiment with the 4 different LLMs, GPT-3, specifically TextAvenue 003, Flan T5, T0, TK Instruct. We also experimented with the various things that I've mentioned, various ways of reducing the size of the prompt. So for example, we experimented, of course, with manually designed versus perplexity optimized prompts. We also experimented with zero shot versus one shot, few shot in context learning setup. So the exemplar that we choose is basically different for each exam, for each sample, right? So the exemplar is chosen based on the immediately previous utterances if available, or else you choose a random exemplar from the entire data set. Okay. For example, if the conversation basically has these 7 utterances, A, B, C, D, E, F, G, and let's say I'm trying to use the recent 4 dialogue history, recent 4 utterances from the dialogue history as input. So my original task would be to, of course, predict G because that's a response, final response. And the current utterance from the person 1 is F. And then recent 4 basically means I'll consume B, C, D, E and ignore A completely, right? Because that's basically not a part of recent 4. It's part of dialogue history. Okay. But then remember, if I'm doing one shot, ICL, then basically I need an exemplar. And for the exemplar, I'm basically going to make use of the previous utterance. So essentially, my target response of the exemplar will be F, and therefore the current utterance will be E, and then my context is going to be the recent for context is going to be A, B, C, D. Okay. So now dialog history again, as I discussed, I could basically use recent K, recent 4, and so on, or semantic K, or I could summarize the entire dialog history using any of those 3 summarization models that I talked about, or I could, of course, use the entire full history. And I want to sort of evaluate how performance versus the size, the prompt size basically play a role in these different settings. Okay. Of course, we can experiment with or without summarized background information. So we don't really use the entire background information as is. We always use the summarized background information because otherwise the background information is actually pretty large in size, specifically for the topical chat dataset. Okay. So how do we evaluate evaluate models under these various settings? Well, we evaluate on both parameters, performance and inference cost. Performance is basically measured using the standard dialog modeling metrics like Meteor, BLERT, and DEB, right? Popular metrics in dialog modeling world. Inference cost is basically measured using a newly proposed metric called as UID, usable information density. Okay. In some ways, it is a very simple metric. It's a benefit cost ratio, right? In that sense. So UID for a metric M, let's say if I take the metric Meteor, right? So UID for the metric M is defined as how much of the Meteor I get versus what is the length of my prompt. Okay, input plus output, basically not just prompt, input plus output. Okay, so the idea is that I want to measure what is the performance that I get per token, right? So per token, because I will be billed per token, so therefore this is my cost in the denominator. And in the numerator, I basically have my metric value, the performance value. Of course, I want to have MH, the metric, to go as high as possible, and LH to go as low as possible, and therefore high values of UID are what are desired, right? Now, I might want to basically give very high importance to the metric and not so much importance to the length, and therefore we have this factor called as A. So A could be basically 1, it could be 2, 3, 4, and so on. So if you want to really give very high importance to the metric accuracy value and not too much importance to the budget or the length, you could basically have higher values of A. But in the next 2 slides that I'll talk about, 2 or 3 slides I'll talk about, we basically keep equal to 1. So which basically means that we give equal importance to the metric value and to the length of the input plus output, so the overall length. But we will also discuss what happens when you change A. Right. Okay. So let's talk about how do the typical input lengths look like under these data sets, right? So essentially, remember we have different settings. So first of all, we have 2 data sets. So therefore, there are 2 curves for MSC and 2 curves for TC. So those are 2 data sets, right? Remember, we also have manually optimized or manually engineered and perplexity optimized prompts. So therefore, we have like 4 curves here, okay? Or rather four plots here, right? So essentially the blue plot, the blue square, the orange circle, the blue triangle, and then the green kite, the green diamond, right? Y-axis basically tells you length in tokens. Input length, this is just input length, plotted, but output length trend also looks similar, right? So output plus input looks similar, okay? And then on the x-axis, what you see is different ways of using the dialog context. So basically, you could basically just use semantic 1, recent 1, semantic 2 or recent 2, semantic 4, recent 4, semantic 8, recent 8, semantic 10, recent 10. Okay, so that's basically semantic K and recent K. You could also use summarized dialog histories, BART-D summarized, Pegasus DS summarized, Pegasus CD summarized, or you could actually use the full dialog history. You could actually also combine, a summary of the background information. So you could do all of those combinations. Now, what you observe is that, of course, complete dialog history is very expensive. So you basically observe that complete dialog history is significantly longer compared to summarized or selected selection forms, any of those selections, recent key or semantic key. Okay. Now, what you also observe is that the few shot, it's not shown in this picture, but it's in the paper. Few shot prompts are typically twice as long as their corresponding zero shot prompts. And that's obvious because we are using one exemplar. So basically, few shot prompts are twice in size compared to zero shot prompts. Okay. Now, the other thing that you observe is that perplexity optimized prompts are not very small. They are basically slightly shorter than manually engineered prompts. So although we tried all that paraphrasing and all that perplexity business, it doesn't really reduce the prompt size too much. Okay. So perplexity optimized prompts are slightly shorter than manually engineered ones. Okay. Also, if you look at the summaries, BART-D versus Pegasus DS versus Pegasus CD, you observe that BART-D summaries are typically shorter. So BART-DS summaries, so BART-D summaries and so essentially Pegasus. I mean, I think, this is sort of slightly incorrect. So what you observe is that BART-D summaries are typically shorter than Pegasus DS summaries, which are slightly shorter compared to Pegasus CD summaries, right? In fact, if you look at it, Pegasus, these summaries, I mean, they're pretty much in a similar ballpark range. But if you look at it, these summaries are 3x smaller, or the 1/3 of the size of the full dialog history. So that's basically quite some savings. But then it has to be, confirmed if they still give you similar accuracies in terms of Meteor, DEB, and BLERT, even though they're 1/3 of the size of the full dialog history. Okay. Another thing to observe is that if you look at recent key or semantic K, well, recent 2 and semantic 2 are more or less in the ballpark range. They are basically almost equivalent in length compared to the summaries. Okay, compared to the summaries. So of course, recent 1 and semantic 1 are smaller, and recent 10 or semantic 10 are much larger. But recent 2 and semantic 2 are almost similar in size to summaries. Okay. Now this is a slightly busy slide, and let me go over it. Step by step. So this is the absolute performance analysis. So this is basically what happens when you try these combinations and you check the performance on MSc and TC datasets. Okay, this is still not about UID. This is not about the trade-off between the accuracy and cost. This is just about accuracy for now. Okay, so let's look at this slide. So on the left side, basically the top pictures are for TC and the lower pictures are for the MSc dataset. So there's two datasets, right? That's that. Now, each of those subplots is for a different metric. So this is DB, this is BLERT, and this is Meteor. So that tells why there are 3 subplots there. Okay. Now, within each plot, what you see is that you have, a similar X and Y axis, or similar legend and similar X axis as in the previous slide. So on the X axis, you have dialog context or dialog histories, representations of them. On the y-axis, you have the metric values, and the legend is basically about zero shot prompt or few shot prompt and manually engineered prompt versus perplexity prompt. Here, you do not see different result. You do not see results for different models. So basically, FLAN T5, T0, GPT-3, or TK Instruct, they are all averaged out to create these pictures on the left side. Okay. Otherwise, there will be too many pictures, and those pictures are there in the paper, but here there is average analysis being shown. Okay. Now, model-specific analysis is actually shown in the table here. So for the 2 datasets, MSc and TC, these are these 4 models, and essentially you have the averaged out to BLERT, Meteor, and DEB scores. Now, these are, again, averaged out across different dialog history combinations and across zero shot or few shot, and also across perplexity optimized or manually engineered prompt. So it's like a large average, but that's what is shown at the top. Okay. So what do you observe? What are the observations, right? So one observation is that GPT-3 really performs very, very well, right? Compared to all of the other models, GPT-3 is the best, and TK Instruct is the worst. So basically, as you see, TK Instruct actually performs the worst. Okay. Zero shot is better than few shot. So essentially, if you look at the charts on the left side, you'll actually observe that typically, and this is non-intuitive, typically people believe that few shot should give you better results, but it turns out zero shot, even in terms of accuracy, is actually better than few shot. Okay. And the next thing is perplexity optimized prompts are actually worse compared to manually engineered prompts. So all the perplexity optimized prompts are slightly shorter, but then performance-wise, perplexity optimized prompts are actually worse than manually engineered ones. Okay. So best results are obtained with full dialog history. I mean, it's sort of obvious that full dialog history should help. So that's that for the TC data set. For MSc dataset also, of course, you get best results using full dialog history. However, even summarized history seems to do really well, which is good news, because if summary actually does really well, and we observe that summary is typically 1/3 of the overall full history size, in that sense, it's really awesome that summaries are actually doing as well as the full dialog history. Okay. Um, Also, what is observed, if you look at the selection kind of method, semantic K versus recent K, semantic K performs better than recent K. In fact, what is also observed is that, so these are semantic K, right? And these are recent K. Similarly, you have that in every plot, semantic K and recent K, right? So what you also observe is that semantic K sort of peaks at 4. So if you basically look at it, I mean, typically the curves look like that. So semantic K sort of peaks at 4. Semantic K, typically you'll observe that, that peaks at 4. This peaks at 4, okay? However, recent K essentially, continues to essentially, increase. So it peaks at 8 or 10. So, in recent K kind of a case, you'll basically observe that it continues to sort of increase and give you better values as you increase, from 1 to 10. Okay. One last observation is that adding this background information helps boost the DB and Meteor, but sort of hurts blurt. So there's no clear signal if background information is useful across all the metrics. For DB and Meteor, it actually helps, but for blurt, it hurts. Okay. Now, this slide is the key slide of the entire discussion, right? So how does the trade-off work between accuracy and the prompt size? Okay, so this is represented as a table, but there are color codes to make it better. Don't really bother about the numbers, but the color codes are important. Okay. So there are results for MSc and TC both data sets. Of course, there is result for different dialog histories. There is results for zero shot, few shot, and there's also results for manual prompt and perplexity prompt, right? And then there are these three metrics. So you can of course compute UID with respect to each of those three metrics, and which is what is basically shown in this table. Remember, these are not actual metrics; these are UID values. So with a equal to 1, basically meaning what is a metric value divided by the length, the input plus output. So very important, interesting observations here are as follows. Typically, manually engineered prompts are better. So basically, you would observe, it may be, in some cases, it may be the other way around, but then in general, you would observe that manually engineered prompts typically give you better results compared to perplexity optimized ones. Okay. Semantic one is the best. So as you observe, if you look at it, for every column, the green color indicates the values are higher and red color indicates the values are lower, right? And that's basically for every column of this kind, for every column within a data set. Okay. So what you observe is that semantic one, this one is the greenest in every column, right? And that basically tells you that semantic one is the best. UID, it decreases as we increase K for semantic stuff. So basically, as you increase K, you observe that, the green starts to become red. Green starts to become red. Basically, that's the observation. Green starts to become red. Okay. Now, for both recent K and semantic K, UID reduces with increase in K. So this is not just with semantic K, but this is also the observation for recent K. If you observe, right, for smaller values of K, the recent K is green, but then for larger values, it becomes red. So this is a very interesting observation that, hey, if you're basically making use of some, recent few utterances, just the recent one utterance is actually better than using several recent utterances. Okay, so that's that. Adding background information to Pegasus DS does not really help. So, the observation is that background information is not very helpful. Okay. Pegasus DS and BART-D actually perform better than Pegasus CD. So there are three ways of doing summarization, and it's observed that Pegasus DS and BART-D actually perform better than CD. And it's sort of obvious because CD is CNN Daily Mail. It's essentially fine-tuned on a smaller data set, while Pegasus DS is Dialog Sum and Samsung kind of data sets. And BART-D is also on Dialog Sum, so that basically gives you better results compared to just Pegasus CD. Okay. Summaries are better than full dialog history. So this is super awesome observation, and in line with the observation on the previous slide, that the summaries typically perform similar in terms of performance to full dialog history, but summaries are much shorter than full dialog history, and therefore from a UID perspective, summaries are better ROI, right? So essentially, summaries give you better ROI compared to full dialog history. And then, as we observed on the previous slide, few shot results are actually worse compared to zero shot results in terms of core performance, absolute performance. And therefore, few shot UID is actually worse than zero shot UID anyway. Okay, so that's mostly the video. One last thing that is left is what happens if I vary this A in the formula, right? So essentially, therefore, we sort of experimented with the 5 different values of A. So we basically varied it as 0.5 to 10, right? So we varied that. And what you see in the table are results for MSc, the results for TCR in the paper. You can look at them later, right? And we basically computed the UID values by varying these values of A from 0.5 to 10. Okay. Now, there are interesting observations here. So as you sort of see, so this is just results for MSc, but and these are results for the three matrix, BLERT and DB and Meteor, and of course on the rows are essentially different ways of encoding the dialogue history, right? So what you observe is that for both the data sets, although the TC results are not shown here, for both data sets DB and Meteor, if you basically observe, as you increase A, remember our hero was semantic one, so you're basically saying semantic one is the best. Semantic one stays best for small values of A. But as you notice, it basically becomes worse for larger values of A. Okay. So again, the coding is the same, in any column. Green basically means the best, and dark red basically means the worst, right? So essentially, as you see, semantic A started off with very good values. It was the best, but then it sort of, it sort of becomes worse, really, as A is increased. In fact, semantic 4 actually starts to become better. Even better are these dialogue summaries, right? So summaries actually start becoming better. Okay. So this happens for DB metric, and this also happens for Meteor. So even in Meteor, if you see, semantic one is good, but then, for larger values of A, these summaries are actually better, right? It doesn't happen for BLERT though. So for BLERT, semantic one really remains the best across different values of A. Okay. So that's that. So for BLERT, ranking is in favor of semantic one or semantic two or recent, and recent one or recent two. But then for DB and Meteor, at least you sort of see this drop in the rank for semantic one as you increase the value of A. In fact, what we did was to come up with this nice, interesting visualization where we actually plot the ranks. So for 0.51 to 5 and 10, and this plot is for DB metric only. So you look at the DB metric only. DB has been trusted as a very good metric in the recent times in the dialogue modeling community, right? And for MSc dataset, what you observe is that, so this is rank one. So recent one is really awesome for small values of A. So for small values of A, it is like the best way of encoding your dialogue history, right? But then it really drops in its rank as you increase the value of A. In fact, what gains in rank is Pegasus CD summary, okay? So summarization using summary, these methods, Pegasus CD or Pegasus DS actually gain, they become really good as you have larger values of A, okay? So that's that. So therefore, the recommendation is recent one and semantic one are recommended ways to summarize the context if the cost is an important factor to the user. If you really care about smaller prompt sizes, use recent one and semantic one. But if cost is less important, right, you're okay with larger values of A, right? So cost is not as important, accuracy is super important. Then longer dialogue summaries like Pegasus CD or semantic 4, longer ones are actually okay to use, okay? Because you don't care about the length, and therefore, slightly longer ones clearly give you better ROI if you're willing to spend more money, but want higher accuracy. Yeah. So that's the insights. So let me conclude this talk. So in this work, we explored the trade-off between model performance and cost for dialogue systems. We basically found that the optimal representation of the dialogue history is one that, or rather we basically have this hypothesis that optimal representation of dialogue history is the one that provides the highest amount of usable information per token. And this is what we used so as to define this UID metric in terms of metric raised to A divided by the overall length. As part of insights, we sort of found that summaries perform better than full dialogue history, and recent K or semantic K is better than summaries in general. Specifically, semantic one is the best from both accuracy as well as UID perspective, specifically if you care about the length or the cost significantly. If you do not care about length or cost, well, you could basically make use of some summaries or semantic 4 kind of a configuration, which gives you really good accuracy, but also increase in terms of length. And one very interesting and a non-intuitive finding was that zero-shot results are actually better than few-shot results, both in terms of overall net accuracy as well as the UID values. Okay, so hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on the homepage. Thank you.